Hello! Testing, 1, 2, 3. Hello, everybody. Welcome out there in TV land. Oh, kitten! Yay! I brought the kitten to say goodbye. So long, auf Wiedersehen, good day. Because this, my friends, is our last lecture that contains actual content, so to speak. This is our last, yes. This is our last actual topic, and we're going to be talking about a field of study that has been gaining a lot of traction in academic circles in recent years. We're going to talk about machine learning. For all, yeah, it has gone by pretty fast, but that's what you get when you have a semester that runs at double the rate. It has been a sprint, not a marathon. But if you have, for both of you that actually went out and bought the textbook that was recommended in the syllabus, the machine learning slides here are based very heavily on the machine learning chapter in that textbook. So if you're looking for a little more reference, there you go. Machine learning is, at the moment in academia, it's kind of the it's the new thing that people are turning to all kinds of different applications. There have been a whole lot of really interesting machine learning projects that have been going on in recent history. And it's like, if you're in some field doing some sort of thing, then you could get a couple of papers out trying to do some sort of machine learning system that applies to the thing that you're studying. And that is primarily because machine learning is sort of quickly becoming an alternative viewpoint to the types of statistical analyses that you often see in scientific papers and some such. Well, you know what they say: time flies. Time flies when you're having fun. Even though it's summer, it went quick. Like I did Orgo over the last summer, and it felt that summer lasted forever. Yes. Well, I'm happy that, maybe we've been having a good time in this course. But on the subject, someone in the chat has mentioned the exam, and perhaps now would be a good opportunity for anybody who is in the chat or watching this right now to ask any sort of procedural questions that they may have with respect to the exam. The exam, just in brief overview, it'll be very, very similar to both of the tests, perhaps just a little bit longer, although not especially. I don't think it will end up being much longer than the tests, to be honest with you. I will give you guys a studying hint right off the top of the bat. When studying for this exam coming up, I think that you should probably prioritize the material that has occurred since the last midterm. Question: is it confirmed that the exam will have bonus questions? You may consider that confirmed. It's either singular or plural. I'm not going to specify. Will it be fetched through JHub 2 as normal? Yes, you may fetch it through JHub 2. You may also fetch it through Avenue. You may access it through all of the normal channels. Yes. So, yeah, when you're studying, I highly recommend prioritizing the stuff that has occurred since the last test. just to review that for you quickly, that includes the material that we covered during the week where we had the second test. So classes, files in week 6, dates, visualization, and databases, and generally speaking, I don't do anything on machine learning because, setting up machine learning is just a long, it's a involved process, and I usually skip it. Sometimes there's like a knowledge question on machine learning, but I haven't really been doing those this semester, so I don't see any reason to start now. Will there be a formal Avenue announcement close to the actual exam, just about all the exam details? Sure. Yeah, I can. Well, I guess it depends on what you mean by the details, but yes, I can put up an announcement on Avenue with respect to that. That would be no problem. To your question, what will be covered, I think I just covered that, so if you want to zip back a couple of minutes, a minute or two, I just went through it. So yeah, machine learning is kind of like the optional extra topic that we are going to talk about, but you're never really going to be evaluated on. So this is mostly for your interest. Yes. Poop. Ah, she's being a stinker. She wants to play. Hello, kitten. Yeah. So that might be some degree of useful. That may have some real life utility for you. So there are a couple of other housekeeping type announcements that I need to make at the present point in time. Number one, for those of you who would like to give some feedback about how this course has gone and whether you liked it, what you didn't like, all of that kind of stuff, the course evaluations will be open this week and this week only. They will be closing, I think, at 5 p.m. on Friday. So, get up while they're hot. Oh, you're purring. I have to purr into the mic. Yeah. So, course evaluations, I always like to take a minute to explain why they're necessary. Because, you get asked a lot of questions, and it's kind of boring. But, so there are a couple of reasons. First of all, it's your opportunity to be able to provide your feedback in a structured manner. And I always, always, always read all of the comments that I get from courses that I've run to try to improve my teaching practice. So, if you have any criticism, I'd love to hear it. Constructive criticism too. Hopefully a little bit of it is constructive. I'd also like to know what is going well and what we should keep doing. I realize this has been a somewhat unusual offering, because normally I would be, there would be a real-life person that you could throw actual physical tomatoes at, but in this particular case, this is an online format where all you get to throw at me are virtual tomatoes, so, perhaps there hasn't been the level of feedback to me that you may have liked over the course of this semester, and this is your opportunity to remedy that. But yeah, so the other reason that course evaluations are extremely important, that sort of pertains to my sort of position within the field of professorial endeavor, so to speak. A lot of people who teach sessional courses are doing so not necessarily looking to make a career out of it, but they're there to, make some money in a particular semester to, teach some courses, do some job-related stuff because, money. Not, certainly that's not all sessionals, but that does happen. However, some of us are actually trying to, go after a career in the teaching side of academia. Yeah, that's the other thing is teaching experience, generally speaking, is looked favorably upon, even if you're sort of going for the tenure track within academia. But obviously, for a teaching track person, it is absolutely essential. So, generally speaking, a candidate, a potential applicant to a teaching track position needs to have some course evaluations under their belt, and hopefully they look favorable. Now, I'm not trying to coerce people into giving me favorable reviews here. I'm just saying I need some reviews, right? Because even if they're not favorable, they are, at least there. And what's really terrible is if you just get no reviews whatsoever. But anyway, even if the feedback is to the negative, then perhaps I can, glean from your comments what I'm doing wrong, and then maybe I can fix it, which would help me shuffle along as well. But it's helpful for me if you fill them out. Anyway, so I have a question. Is visualization going to be covered on the exam? Because I noticed it wasn't leaned on in the last assignment. No, yeah, that would be a fair statement, wouldn't it? Let's put it this way. It would not be a heavy element of the exam if it's in the exam. I'm not going to confirm or deny whether visualization is in there. Oh yeah, and perhaps it should be mentioned that because this is a course evaluation that is going on through the proper and normal university channels, every piece of this is going to be anonymized. So I'm not going to be like looking through the comments, looking for all the people who gave me a bad rating and specifically rigging it so that their exam is twice as hard. No, that's not how it works. And besides, with respect to that, it's a computer that's doing all the marking anyway. So about as objective a marking standard as you can get, really. But anyway, so that's the situation with the course evaluations. There is one other piece of information that I need to disclose / divulge to all of you at this present point in time. So test 2, for various reasons, the auto-grading scripts for that evaluation have been significantly more difficult to actually get right than I had anticipated. I am, in fact, still working on them. I have received numerous emails that in the last in the last revision, a bunch of people who had actually gotten the bonus marks on the Ackerman memoization question, a lot of people who got those marks ended up not getting those marks in the revised version, and I can explain to you why. There's this interesting little phenomenon that happens with it, where if you used a memo that's included as a default parameter, oh, quick question. Do we need to install SQLite on a local machine? No, you do not need to install SQLite on a local machine, which means that you can expect it to be occurring through the Jupyter interface, which means you may want to brush up on the bits in that slide that have to do with how Python can run SQL scripts or queries. Big ol' wink, because that's a hint. What was I talking about? Let's see. Yes, test 2. So this is what was happening with test 2. For whatever reason, it seems as if the memo is kept between separate executions of Ackermann memo. So the memo isn't resetting between subsequent runnings. If you were using a thing with default parameters before, the problem with those test cases was, the test case assumed that you were using a default parameter that was not asked for in the question, which obviously is wrong, and it was giving it an empty dictionary each time the thing was run. So that was, in effect, resetting the dictionary. However, because that value is not being kept, because the memo is being kept between subsequent runnings of Ackermann memo, since it's not being reset anymore, if you're not, if the memo isn't reset, then you're obviously not going to have the correct number of recursive calls, because, your memo is already partially populated, so the maximum number of recursion iterations that was supposed to occur wasn't in fact occurring, and since this was a strict test of equality for the number of recursion iterations which were occurring, a bunch of people who had correct solutions were failing like 3 out of 4 of the test cases because the memo wasn't being reset between test cases. So I was sort of experimenting with a solution to that problem this afternoon, and I haven't quite got it nailed down just yet. I'm continuing to work on that one, but this will be a thing that only causes people's grades to increase. So if you were in that camp where the non-resetting memo ended up costing you grades, in the new version that will not be the case. However, again, still ironing out the details. Hopefully that's finished by tomorrow morning, because, I've got the exam to finalize as well. But anyway, I realize I begged your indulgence for the test 2 last week, and unfortunately I'm still in the position of having to beg your indulgence for it this week, so we'll get this sorted in the end. But anyway, that's about everything I have to say with respect to bookkeeping stuff, so I think with that we might move on to the actual lecture material for today, if nobody has any objections. Do I hear any objections? Why is he listening? The chat is coming over his phone. Yes, okay. Good. So, let's speak about the big bad spooky AI, the singularity. We are talking about HAL 9000. We are talking about Skynet. We are talking about whatever that one was from iRobot, whatever it was called. Anyway, machine learning. It's not as scary as it sounds. So machine learning basically boils down to statistical analysis over large data sets. So, we'll be talking about linear. We'll have an introduction, rather lengthy one for this type of thing. Then we will get into some types of machine learning. Sunny. Thank you. Except it's Asimov, so it was probably SNE, but it was pronounced Sunny. He liked that trick. Anyway, so, machine learning. What is it? Important to have definitions. Machine learning is a computer system whose performance on a particular task improves as it gains experience. Alternatively, machine learning involves observing a set of examples, the training data, and then attempting to conclude something that generalizes the data. Many statistical methods are an example of machine learning, for example, linear regression. So, artificial intelligence is a very interesting field in the field of computing, computer science, software engineering, all the rest of it. Essentially, whatever interesting developments are made in the AI community get spun off and become their own field or their own application at the minimum. So we all have, it's really quite interesting that everybody kind of just takes for granted now that we have reasonably robust voice recognition software. And it's built into, your magic rectangle that everybody has in their pocket. So voice recognition started off as a subfield of artificial intelligence because it was reasoned if you were to create an artificial being that is capable of interacting with human beings, a good first step to that interaction with human beings is the ability to interpret what they say. Human beings are speaking animals, and our, vocalizations are primary in their intent and meaning. So it's really not possible to have a meaningful interaction with a human being, at least one capable, I can hear people objecting right now, but what about sign language? That's not speaking. And I would say, yeah, it's not speaking, but it's language, right? So it's useful to be able to interpret human language, be that, sign language or speaking. You would, with respect to sign language, you would be talking about image recognition, which again was a subfield of artificial intelligence that kind of spun off and became its own thing. So, yeah, and machine learning is kind of doing the same thing, at least with respect to this this second definition of it. Where it's heavily involved with statistical analysis and trying to derive mathematical generalizations. But yeah, like the definition that you would have of machine learning that's more in line with, shall we say, the science fiction interpretation of the phrase is a computer system which gains performance as it gains experience. So the question is, what constitutes experience with respect to a computer? In the case of machine learning, when we're talking about experience, what we're talking about is numbers, right? Experience basically has a one-to-one mapping onto the size of the data set that you use for the statistical analysis that you perform. Pardon me. So, I think most of you should have a sufficiently robust understanding of statistics from a high school level, or, if you've taken statistics here at the grand old school of McMaster University. Generally speaking, there is a proportional relationship between the size of the data set that you are operating your statistics over and the reliability of the conclusions that you can derive from said statistics. And this is you can map that one-to-one onto machine learning experience for the data set and machine learning performance for the quality of the statistical conclusions that you can draw. So, yeah, in essence, if that makes sense. one must keep in mind the other maxim of statistical analysis, that correlation does not imply causation, right? So just because we have a correlation in our statistical data, that does not necessarily imply that one causes the other. It's actually a non-trivial matter to determine in any particular correlation relationship between two, variables. It's not straightforward to decide which one is influencing the other. So, statistics are just kind of tricky, and this is about statistics largely. So, we have a couple of different types of machine learning that we use in our present context. We have supervised learning, which is where the data set essentially already knows what it should be interpreted as, and you want to have your computer algorithm come to a generalization that produces the pre-known properties of the things that you're giving it in. So this is an example of having training data. So a classical example with machine learning applies to image processing. So a thing that you can do with machine learning is you can give it pictures of cats and dogs, right? Give it a large database of pictures of cats and dogs, right? You have all of these, .png pictures, and you have each one labeled as being either a picture of a cat or a picture of a dog. What the machine learning will attempt to do is construct a mathematical model of the, it'll do various mathematical tests on the pixels that constitute the picture, various visual, image processing techniques. It'll apply these, and it will try to determine for itself some sort of mathematical model, which may be an equation, that will reliably produce the same label as, or produce the same result as the label that's applied to each picture. And then, once you have trained the computer to recognize the difference between a cat and a dog, or a picture of a cat and a picture of a dog, because that's not the same thing, right? Recognizing a picture of a cat and a picture of a dog is not the same thing as knowing what a cat and a dog is. The idea is that you could take this computer algorithm and apply it to unlabeled data, and then get it to be able to tell you, distinguish pictures into cat and dog pictures with some, some percentage of reliability, which usually increases with the number of, with the volume of trading data that you have available to the algorithm. So I realize that was a bit of a word salad. Are there any questions about that? In the meantime, I will just quickly explain unsupervised learning. So in unsupervised learning, the computer is given its inputs, its training data, not exactly training data because you're not training it into doing any particular thing, you're just giving it data. And the computer's goal is to identify a structure or some pattern in the data using one of the methods we're about to discuss. Classification is a good example for this. So in terms of applications, we've got a number, like as I mentioned earlier, the number of applications that are being found for machine learning are very, very, very large. So, you know, your YouTube recommendations, that's a type of machine learning algorithm. Recommendation systems in general are, generally speaking, machine learning algorithms. Pardon me, I'm going to sneeze. So, with respect to the, like, let's take YouTube's recommendation system, right? The data that is being fed into that algorithm is, well, there's quite a lot, really. What videos you have watched, how much of them you watched, whether you watched them to completion, and also the viewing behaviors of other people who have watched similar videos to the videos that you have watched, right? And if you take all of that data, which is a heck of a lot of data, and you aggregate it together, you can, with a reasonable degree of accuracy, it turns out, YouTube can predict the type of video that you would be interested in seeing based on your previous watch history and the watch histories of people who watch the things that the type of thing that you like to watch. So this can be somewhat problematic because it kind of turns YouTube into a bit of an addictive substance. However, whether or not having too good of a recommendation system constitutes an evil use of technology is, again, sort of to the side of whether it's possible to do something using technology. So, normally we try to do supervised learning with classification. However, there are classification systems that are unsupervised. There are usually two or more classes or labels that we're trying to classify things with, and our goal is to come up with a rule that classifies inputs based on the classes in the training data. So classification is this example that we're going to get to at some point during this lecture. So, regression analysis. Believe it or not, linear regression is a form of machine learning. It is also a type of supervised learning. In regression, output values are continuous, for example, real rather than discrete when you're trying to do classification. The goal of a regression analysis is to come up with a rule that predicts the output values based on the values in the training data. I'm sure everybody in the chat knows what linear or any type of regression is, really, so I'm going to try to move through the regression stuff reasonably quickly. So, clustering analysis. This is cool. Clustering is a type of unsupervised learning. The goal is to divide a set of inputs into groups. Groups are not known in advance. What you want to do is generate groups based on their similarity. And with respect to what we consider to be similarity, what we're talking about is proximity, Euclidean proximity, but we're going to get into that. So in this particular instance, we have all of these gray squares, and you can see we've got 3 groups roughly. So our goal would be to have a computer derive via its own interesting and arcane mechanisms the same grouping as we as humans would assign it. Or it may even be interesting to have the computer come up with an entirely original design. I remember a while ago, I saw on a television program or something of that nature that some scientists had a machine learning algorithm iterate and produce frames for drones Although at the time we called them UAVs, or quadricopters, if you were the kind of person who likes to give things long names. So what happened as the iterations of this frame for this thing iterated, you ended up with a thing that looked more and more like a frog's skull, just with like large spaces in between loops and stuff like that. But yeah, it's cool stuff. So here is a classification example. We have a list of famous people, both American and French, and we have a list of heights in centimeters and labels A and B. In supervised learning, we give a dataset of feature vectors, each with some labeling. Given a new feature vector, how would you classify it? That's the question. So these are the features: name, nationality, height, and label. What you consider to be a feature and what you consider to be an identifier. That's sort of, that's left as an exercise to the reader, I suppose. In this particular case, you could very easily argue that the name is the identifier and that the feature vector consists of nationality and height, because we're not really interested in deriving a label from the name of the person, although that might be an interesting analysis as well. So feature, label. The two features taken together form a vector for each entry. So if we had some additional person, Thomas Jefferson, nationality is American, height is 189 centimeters, what do you guys in the chat think that this should be? Should this be an A or a B person? Assuming chat is awake, of course. Assuming I'm actually receiving the chat messages. Oh, there we got one person. A person has said A. Now we've got more people. Everybody is saying A. So this is kind of an easy one, right? With this particular one, if you notice, you don't even have to really look at the nationality here. If you take a look at the A's and the B's, everybody who's kind of on the shorter side is a B, and everybody who's on the taller side is an A. Now, since our height here is actually precisely the same, actually our feature vector itself is identical to one of our entries. It turns out that Thomas Jefferson and George Washington, in terms of this chart, were the same person. Since George Washington is labeled as an A, it is entirely likely that Thomas Jefferson will also be an A, which I think he is, although there should be a slide that says that. But anyway, so clustering analysis. In unsupervised learning, feature vectors are given without any classification. Clustering is used to try to find clusters of similar feature vectors. But our problem is, how does one go about measuring similarity? What does it mean to be similar? Important question. So, number one, this is in math. Everything is math in programming. So, in order to do this, we're going to take our features and convert them into numbers. Then we will compute the distance between the vectors that we have numeratized in order to determine their similarity or dissimilarity. So the closer two points are together in multi-dimensional feature vector space, the more similar they may be. And the further apart they are, the more dissimilar they are. So, here is an example data set. We will talk about the similarity of animals within the animal kingdom. So, column 1, that's the animal's name. We're not going to consider that to be a feature. Columns 2 to 7 are feature vectors. And, that's a cutoff there. Given these features, we need to decide if, my goodness, a boa constrictor is a reptile or not. That's what that's supposed to say. I am very disappointed. Anyway, so we've got cobra, rattlesnake, boa constrictor, alligator, dart frog, salmon, and python. We have the features egg-laying, whether or not they have scales, whether or not they are poisonous, whether they are cold-blooded, the number of legs that they have, and, of course, the label, is it or is it not a reptile? So, first we convert each animal into a sequence of numbers. So, if we make true into 1 and false into 0, then we end up with feature vectors containing a bunch of 1s and 0s. Python! Yes. So, now I'm going to make an argument here, which, hear me out. With respect to the number of legs category here, all of our elements have either 0 or 4 legs, right? So when we're calculating distance, as you'll see in a few slides, that's going to show up hugely. That's going to really heavily skew the results, because anything that has legs or 4 legs is going to automatically be removed from the rest of them by a distance of 4. And since we have 4 other feature vectors, the presence or non-presence of legs has about as much influence on the clustering analysis as it currently stands as all of the rest of the feature vectors put together. Obviously, if the difference was maximal among each of these other 4 feature vectors, the maximum distance will be 4. All trues versus all falses. That's 4 times 1 plus, minus 0 is the difference, and that's 4. So, this is my recommendation for this particular instance. If you take the legs and you divide each element of the category by the maximal element of that category, what you essentially get is kind of like a percent true, if that makes sense. But anyway, that will knock on the head that additional effect that's produced by the fact that the alligator and the dart frog are getting credit for each leg they possess, not just simply the presence of legs. But anyway, you'll see how that sort of skews the results in a slide or two. So, measure of similarity, the Minkowski distance. So, this is a generalization of Euclidean distance. It's also called the Taxicab Metric. The reason that it's called the Taxicab Metric is if you imagine a city, such as New York City, why not? If you imagine it as a set of roads and a set of city blocks, I think New York City is used because the grid is very grid-like. Modern city design actually dictates that that's not necessarily actually the most efficient solution to the organization of roads, but it's what they used back 100 and some odd years ago. Anyway, you can't drive through a city block. You can only follow the streets, right? So what that means is that the taxicab distance is not Euclidean distance. It's not, you don't use Pythagorean theorem in order to get at it. So if we take this grid here, this green line, which passes through a bunch of city blocks, that would be your, as calculated by Pythagorean theorem. So each one of these red, blue, and yellow lines is actually an equivalent distance, right? If you travel up by 1, over by 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., etc. So what you're actually doing here, rather than calculating the via Pythagorean theorem, all you're doing is you're taking the two vectors and subtracting them from each other, essentially. So, in this two-dimensional example, what would the distance between these 2 points be? Please feel free to enter your answers into chat at this point in time. How far is it from this one to this one? In taxicab or Minkowski distance. We're getting a bunch of people saying E, 7. The E's have it. The correct answer is 7. 1, 2, 3, 4, 5, 6, 7. Very good. The Euclidean distance between these 2 points is, of course, 5. Because 4 squared is 16, 3 squared is 9. You add those, that's 25. Square root is 5. So the Euclidean distance is 5, but the Minkowski distance is 7. I know you guys maybe wanted to answer that, but I thought it was, Anyway, so if we create a Python script to calculate Minkowski distance, it would look something like this. Def Minkowski dist v1, v2, taking p. P is, of course, what is it again? The number of parameters. So, or the size of the vectors. So distance is equal to sum of the absolute value of v1 at I minus v2 at I to the power of p for I in range length vi. Return the distance to the power of 1 over p. So, if we want to model some of these animals that we've been constructing these feature vectors for, we can do that with a class now that we know how to do classes. So, we have name features, self.name, self.features, and distance is just returning the Minkowski distance between self.features and other.features. If we enter our data in, create a bunch of classes for it, Cobra is equal to animal, animal name of Cobra, it's a 111101, 111101, etc., all down the line. We can construct a list of the animals which we may use. If we plot this, that is a terribly small thing, hup, 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 we can see that we can actually plot this algorithm. Takes each animal and calculates the distance from each other animal. So, you may see that rattlesnakes and cobras are the same animal. Alligators are 4.24 away from cobra. A boa constrictor and a salmon are similar at 1.41. Salmon are quite similar to snakes, according to this. So yeah, that's what you can use to determine the distances between things. So that kind of brings us into our first break. So we'll resume our discussion of machine learning at the termination of the break. We will resume at 6:30. See you then. Hello. We're back. I should see what chat is doing. Boop. So, I have a question from a Shane Whitmore. I have seen some concerns on the Max subreddit regarding privacy issues in regard to the software being used for proctored exams. Is our exam still open book and not proctored? That is correct. Your exam is open book and not proctored. So there you go. We will, however, be using our plagiarism detection software to check the exam submissions in post to make sure nobody has been cheating or doing anything nefarious. So there you go. Question: why do we return dist of 1 over p? So that is a congruency with the that's just so that it implements the formula right here. So I don't know, man. I just work here. Sorry. Anyway, so let's talk about linear regression. Regression is a type of supervised learning. Our output values are continuous, for they are real numbers rather than being discrete as they were in this case. Our goal is to come up with some rule that predicts the output values based on the values in the training data. So you can see that we come up with this line which describes the data. It finds the line of correlation. So suppose we have n two-dimensional data points. And the purpose of this example is to demonstrate the procedure for doing a supervised machine learning system. So the procedure is generalizable, even if linear regression itself is kind of a boring thing, a boring type of statistical analysis to do. What's important from this example is the methodology. So it's kind of like a double-blind study. We want to find a function f that predicts y from x. In linear regression, we are trying to find a linear equation that approximately fits the data of the form y is equal to cx plus b, c being the coefficient and b being the intercept. You may have also seen y equals mx plus b. So does the Minkowski distance only work for clustering, or is it used for everything? Clustering analysis, classification analysis, I'd say as well. Anything discrete. So to answer Mars Lettuce's question, the Minkowski distance is used to find distances between things that have discrete values. So, non-floating point numbers, We have features. These are discrete. Things can either be true or false. And if that's the case, then there's no such thing as a half-truth, at least in computers. So there's no point in trying to do a regular Euclidean distance on it. That's why we use the Minkowski distance. Hopefully that answers your question. So, where were we? Yes. So, our regression procedure. Number 1, obtain the data. Number 2, divide the data into 2 sets, a training set and a testing set. Run linear regression on the training data to get a proposed coefficient and intercept. use the proposed coefficient and intercept to predict the y values of the testing data from its x values. Then, we must measure how far the predicted y values are from the real y values in the testing data set. So, in summary, we get our data, we have our testing group and our training group. The training group is what's used to generate the regression, and the testing group is used to determine how good our training was. So, measuring how far the predicted y values are from the real y values, we will use mean squared error. Let y, lowercase y to yn be the real y values. Let capital Y1 to yn be the predicted y values. The error of any particular set y1, both y1s, y2s, the error of any particular sample I is lowercase yi minus uppercase yi. So the real value subtract the predicted value. The squared error is, of course, just that error value squared. And the mean squared error, is the average of the squared errors of all of the samples. So, linear regression attempts to find proposed coefficients and intercepts that minimize the mean squared error. This is called least squares estimation. The coefficient of determination, aka the R-squared score, is a measure of the goodness of fit of a regression model. R squared equals 1 implies a perfect fit, and R squared equals 0 implies no better fit than a horizontal line. Or indeed, any line, really. We will be using scikit-learn for linear regression and other machine learning in Python, at least within the context of the slides. So, if you have installed Anaconda, you will have scikit-learn. If you have it installed on JupyterHub, you will have, or if you are using JupyterHub, you will have scikit-learn. If you wish to install using idle or Jupyter, use any of the 3 command line options if you know how to do so. If not, just download Anaconda. So, just to remember, we need to obtain the data, divide the data, regress the data, get the proposals, and then use the testing data to see how well we predicted the testing data. So, in order to obtain the data, we need a list of XY points. This code generates a random sample of data for us to play with. So, I don't think that we've actually had we haven't actually looked at the random library. We haven't actually looked at the random library in Python just yet. So that might be worth taking a look at, eh? I should probably talk a little bit about. I'll just take on the end of 10. I should probably talk about what randomness means within the context of a computer. So, and some of you will have already heard this, but with computers are deterministic things, right? There's no quantum superposition way down in the computer that has any effect on the values that are stored in various memory bits inside of a computer, at least not when the computer is operating optimally. So, essentially, your outputs are based strictly on the inputs and whatever the state there is in the computer. This means that there is no such thing as a random value generated by a computer. computers are incapable of true randomness. Flat out. There is nothing you can do about it. So, you may be saying to yourself, but Mr. Professor Moore, sir, I play video games all the time that have randomized elements in them. Flappy Bird, for instance, if this thing that you were saying that computers cannot generate random numbers was true, then first of all, why would you be able to import a random library? And second of all, how is it that I may be able to play Flappy Bird with random positions of the pipes that the Flappy Bird flaps through? So, I would say to such a question, while you may not have true randomness, you do have pseudo-randomness. So, in a computer, when you ask for a random number, it gives you some number that is based on some sufficiently convoluted calculation that there's no, perhaps you could say, there's no logical connection between the input and the output because you've run it through so many calculations. However, all random values generated by a computer must be generated from a quote-unquote seed number. So this is for all of my my Minecrafter people who are watching this right now, if you've ever played Minecraft and you've ever gone into the advanced world generation settings, you'll notice that it gives you the opportunity to specify your, I forget if they call it a world seed or a random seed, but when you generate, and some games allow you to do this, the purpose of them doing that is to allow the user to be able to generate the same world a couple of times, within certain limitations, of course. I'm not sure if you enter the same seed twice, you'll get exactly the same Minecraft world. It seems like it might be possible, but then again, you never know. So, the seed that you enter in during world gen in Minecraft is the seed which the random number generator uses to generate random numbers. Typically, in some random seed situations, every time the seed is used, you increment that seed by 1, and that is a sufficient difference for the function that calculates the random number to have some, like the next random number bears no mathematical similarity to the previous number, at least not one that is detectable by not one that's detectable by human beings. But that's the thing about pseudo-random numbers. While the pattern can be so convoluted that no human, even the most mathematically gifted human being on the planet, would not be able to predict the next number from the previous, that doesn't mean that there isn't a pattern to it, right? And because it's only pseudo-randomness, there's always a pattern. But anyway, one clever thing that a lot of random number generators do is they pull their seed value from the system clock. Because the system clock is a number that is constantly changing, and not only is constantly changing, but is different at every point in time, it reads something different. That adds a layer of randomness to the pseudo-random number generation that you can get a better random number than by the incrementation method. But anyway, that's, I think, enough about random numbers. If you're interested about random numbers and how to generate them and how to use them, please consult the Python documentation. Anyway, So we import random. We use random.random. So what random that will do, random.random, will just generate you some number between 0 and 1. I think it's inclusive of 1 but not of 0, but that, it'll never really hit either, so it doesn't really matter. You can also specify a random number within a certain range. You can specify a random number within a has to be a int as well. So if we say x is equal to 0 for I in range 100, random x is equal to x plus random dot random, print x. You can see that this is a lot of numbers, and each time we generate it, it's different. There you go. However, interestingly, if you take the average of all of these numbers, so the sum of that divided by the length, you'll see that you get something reasonably close to 0.5, meaning that the numbers are being generated in a linear distribution. And if we up the number, you can see, just because, just from the laws of statistics, our average gets closer and closer to 0.5. On average. But yeah, so that's randomness. You can find cool libraries to generate numbers in like normal distributions and all kinds of fun stuff if you want. That can be useful if you're looking for that sort of thing. Anyway, so we generate our numbers. Data is an empty thing. We y is equal to round coefficient times x plus y spread. So we're going into this knowing what our coefficient that we're going for is, and how many samples we want, and what the spread of that data we want it to be. So yeah, and it's just a linear distribution within the spread. And as x increases, we are going up by the coefficient value. So the next thing that you do is you take this data that you've generated and you divide it into two data sets, the training and the testing data. This is reasonably simple. However, not quite as simple as you might think, because there are good and bad ways to split up data. So one might say, well, could we not simply take the front of the list and call that one, and the back of the list and call that the other? And the answer is, well, that would be nice, but no. In fact, no. The problem with dividing up your data on that type of a basis is that if there is any bias in the data that has anything to do with the order in which the data occurs, then you're going to inadvertently include that bias. Whatever bias is in the training set, that's going to be included. So generally speaking, you want to avoid biasing your data. Now, of course, in this particular example, our data has been generated through a random number generator and is therefore not biased in any way, form, or fashion. At least, at least not in any manner that is interpretable to mere humans. So it's not so much of an issue for this particular example, but, keep this sort of thing in mind. So what we're doing here is we are using random.sample to generate a number of, basically generate a list that is telling us whether whether we're going to add any particular value to the training or the testing data. You could also do this reasonably easily with where's my Jupyter? There we go. You could do this reasonably easily with a, if back to my C days, Octothorpe. If we have testing data, why is everything red? Did I not close a thing? Testing data and training data similarly. Is there a problem here? No, it's just red for some reason. Okay. If for element in X, if random.random is less than 0.5, test equals test plus lm, or test dot append lm, else training dot append lm. So it's not actually a strict requirement that your testing and your training data have the same number of elements in them. There, type error. There. So you can see we've got two sets. Oh, let me just knock that down to something reasonable, eh? So you can see we've got two sets of data here. They're not necessarily the same size, but they don't have to be. On average, if you were to generate this testing data, if you were to generate this division a number of times, it would sort of they would be approximately equal over the course of history. Like those ones are approximately approximately evil. Yeah. Anyway, so boop. So here is a randomly generated data set split into training and testing data, etc., which we have done. So if we wish to actually plot this data, yeah, so it's generating two. Okay, well, we're getting random X and Y components here. Just adding in things very quickly. Adding things, oh my lord. There we go. A scatter plot. Now, this is, of course, just kind of random data. If we were to add the coefficient and stuff like that, that would be better, probably. So, you know, I times 0.2 plus or that'd probably be more like it. That should introduce a sufficient, yeah, so that maybe we can make it a little stronger. Increase number of points. You can see why you would want to encapsulate some of this in functions now, eh? Yeah, so there you go. Data. So scikit-learn has a number of regression tools, but we're going to be using linear model.linear regression. So, oh my goodness, there. From scikit-learn, choop, chaboop. Let's just not print all of that data anymore, shall we? We have our regression. So the regression is actually an object, right? This is object instantiation. We wish to fix a 1D array on X-train. So there we go. And then we wish to fit our regression for X-train and Y-train. We can then access our coefficient and intercept that have been calculated via the linear regression using dot syntax, as you might expect. So it's calculating. Name error. Oh, right, it uses a function that's on the next slide. Lovely. So scikit-learn expects us to be doing more complicated stuff than we are. So we just have to do this one little thing where we reshape. We convert a basic 2D regression into a, something that would fit a larger one using that function. So we'll just stick it at the top. There we go. So our estimated coefficient is 1.9931, etc., etc. Our estimated intercept is 0.57. So if you take a look at what's actually going on here, our random range would be between 1 and 0 when x is equal to 0. So so the actual average x-intercept would be 0.5. So this is actually doing pretty dang well. The slope that we gave this data was, of course, 2, and that's a reasonably good estimate of that one as well. So there you go. It's actually doing pretty well. If, for example, we were to introduce some sort of offset of, say, perhaps, 100 or -7, you can see it's -7 plus the 0.5. So negative 6.5 is a pretty good estimate again, and we're getting a pretty good slope estimate. And obviously, if you increase the size of the data, then you're going to get more accurate estimates. We can, of course, plot this. However, we may be more interested in measuring how far our predicted y values are from the real y values in the testing data set. So we can, from skKit metrics, import mean squared error and R squared score. Copy that. So our y values for our testing are going to be, of course, x test is this guy, and y test is that guy. And our y prediction, of course, that has to be calculated for point in x test. There we go. Y pred is an empty list. Then y pred is equal to regression.coefficient times p plus regression.intercept. Don't forget the underscore. There we go. So our mean squared error is 0.07, and our R squared score is 0.86. So if you remember, an R squared score of 1 implies a perfect fit. So we're doing a pretty good job. And just for the sake of interest, let's put that little old regression line on our plot. So there you go. Very easy. So that's how you train data. Linear regression, again, probably not the most interesting thing you can do with this, but the methodology is sound and transferable to a large number of different situations. So you can do linear regression with multi-dimensional data, which you might have known already. You can even do it you can do it in hypothetical large numbers of dimensions. But this is what it looks like in 3-dimensional data. And ignore this where it says workbook on Avenue. There's no workbook on Avenue for it. So your data is in a 3-dimensional space, and of course, when you're performing a regression analysis, the function that you generate has one fewer dimensions than the number of dimensions that the data has, right? So in a 2-dimensional space, you get a line. In a 3-dimensional space, you get a plane or a surface. In a 4-dimensional space, you would get a solid. You would have a regression shape, which would be cool. Anyway, so let's move on and talk about classification. So this is usually a type of supervised learning. There are more classes. There are 2 or more classes or labels. Our goal is to come up with a rule that satisfies inputs based on the classes in the training data. Going back to our animal model that we were talking about previously, this is basically, we're going to do this in code now. So, conversion, well, I don't know, I think maybe, well, we'll see. So, of course, if you remember, the first thing that we do is we convert each of these animals' features into a feature vector with some value representing each feature. Our classification procedure is obtain your labeled data, construct your feature vectors for the labeled data, divide the data into 2 sets, a training set and a testing set, train the classifier on the training data in order to develop the model, use the classifier, get out of my face, jeez. Use the classifier to predict the labels of the testing data and then measure the accuracy. So, when you measure the accuracy of the predicted label on the testing data, you basically have 4 possibilities, which, because everything is discrete now, we're not necessarily dealing in the realm of, R-squared values and mean squared errors and that type of quantifiable thing. You're mostly going to be testing binary results, although not exclusively. So when you have, and this actually works for like medical tests as well. So in fact, we can relate this to current events. If the test came out positive and you actually had the thing that was testing for, so for example, if you have COVID-19 and your test comes back as positive, that's a true positive result. If you have COVID-19 and your test comes back negative, that's called a false negative result. And apparently, it turns out that with the tests that we currently have for COVID, false negatives occur about 20% of the time, 1 in 5, which is probably, like, that's not necessarily, that makes a certain degree of sense because they swab the inside of your nose to test for it, and if it's not in your nose, but it's elsewhere in your body, then obviously testing your nose isn't going to do much. Anyway, if you do not have the COV, but you test positive for it, that is a false positive. To my understanding, that's not really a problem with the COVID-19 tests that we have. And if you do not have COVID-19 and your test says that you also do not have COVID-19, that is a true negative result. I wonder if I'm just not getting chat or if nobody's been chatting. No. Okay. It's been a while since I heard. Just want to make sure you guys aren't dead. So, we will, in these slides, we will use the Natural Language Toolkit for classification of text and more general data in Python. If you wish to install it, you can install it on your own idle or Jupyter installations using any of the following commands: pip3 install numpy scipy scikit-learn, etc., etc. Some natural language toolkit operations require that you download some additional data before you can do that. This is easy to do inside Python. The error message tells you what you want to do. The code examples include these commands where needed. Need more memes in the lecture. Oh my goodness. If you have to think about it this long, then it's not a meme. I don't know, how about Dat Boy, the frog on the unicycle? Anyway, never really got that one. Anyway, so in order to obtain the labeled data, well, this will be a thing that you get from whatever source you have for your data. Deep fried memes can't transfer the vid. Yeah, sorry. I know it's a little bit dry, but you know, it is here and I am covering it. Gosh darn it. Spicy memes. Meme. Trying to think of a meme. My goodness, my brain is just kind of dead today too. Mechanic. There. I don't know. Anyway, when you get your data, the data should include labels for each of your data elements. Think the cat versus dog picture example from earlier. For the natural language toolkit, we need a list of each element. Each element of the list is a tuple containing two things: a dictionary of feature names and values, and a label. So if you remember, the way that we did our animal class before is we just had a list that was the features, but now we have a set of feature names, which are all strings, and we have a dictionary which corresponds to the feature vector that was being taken in before. So we have a features as dictionary method, which we can call on our animal to extract from it the dictionary. This way we don't have to enter the labels in each time. We can just enter the values in. So there you go. The code on the previous slide is a somewhat organized way of generating the following labeled data for classification. All of these dictionaries, all of these values. So, we wish to then divide the data into two data sets, the training and the testing set. Best practice is to split the data into two data sets, the training and testing set. If, of course, with this particular example, we really don't have that many of them, but you know, if we had only one data set and came up with a model for that data set, is not surprising that it would predict the data set well. The real test is if we can predict another data set well. So this is a Python function which will split the data. Number 4, we want to train a classifier on the training data to develop a model. From natural language toolkit.classify, import naive Bayes classifier. Training data is equal to feature sets minus the last one. Classifier is nltk.naive Bayes classifier.train training data. So this is how you invoke and generate your classifier. It's very cool because it handles it all for you. Once we've run the trainer, we can learn a little bit about the model it's developed. Most informative feature. Legs. You don't say. Haha. It predicts with a 2-to-1 ratio, which is good. We can run the classifier on a feature vector to see what it predicts. So for t in testing data, predictions.append classify t at 0. So if you wish to create a prediction, you use the classify method, on a feature vector. So notice that the testing data, of course, is in this form, so you'll want the first argument of that tuple, which is just the dictionary. We can then print our predictions. We can also measure the accuracy of the predicted label on using an ltk.classify.accuracy classifier, and then we have the testing data. We can just shove the testing data into it wholesale, and that's how you do. So that's cool. Yeah, we'll have time to do this. I was thinking that perhaps we wouldn't have time to actually do this, but I think we actually do. So let us grab some code. Oop, I said, oh, is this a picture? Oh, no. That's a picture. Dang it. Oh, okay. We're going to do this. We're going to do this, guys. Class. Animal. Def init. Self. Name. Features. Reptile. Self.name equals name, predictably. Self.features equals features. Self.reptile equals reptile. Oop. Def features as dict. Self feature names is equal to a list. It's really hot in my house for some reason. Egg laying. Scales. Poisonous. Oh, I've got a meme for you. You've met with a terrible fate, haven't you? You found out that the slides you can't actually copy and paste from them. And legs. D is an empty thing. For I in range, length self dot features D at feature names I is equal to self.features at I. There we go. Return D. Good. No syntax errors. Get out of here, bookmarks toolbar. Nobody asked for you. My word. So question, I usually use the assignments to help with my learning. Since we don't have an assignment for the last couple of lecture content, is there something I can do to help supplement my learning? Well, if by learning you mean studying for the exam, then I wouldn't worry too much about it, because I'm not going to test this stuff off. I'm not testing this stuff on the exam. However, if you just want to learn the stuff, I think I might be able to dig out some of the old materials and then post them up on Avenue. However, please send me an email to remind me of that, and I will do that. Anyway, it's now the break. So I think what I'm going to do is I'm going to work on this a little bit during the break, and then when we come back, I should have all the code done. So, see you in a few minutes, folks. Hello, everybody, and welcome back to our show. To your question, does anybody know where the doodle pads are posted? They are not yet. I will post them. Please send me an email. Please email me about it to remind me, and I will do it. Yes. So anyway, I entered all of this stuff in over the break, and this is the feature sets that get returned back. So we can continue from that point. We want to, of course, have our method of splitting the training data with this function. Yeah, that's not a bad idea. The Trump tweets.json does have quite a lot of data in it, which you could probably do some interesting stuff with. And even a bit later on, we'll be talking about sentiment analysis, which might also be an interesting application for the Trump tweets, because that's it's also a thing you can do. So we shall apply our naive Bayes classifier. Copy that. Normally this kind of thing takes a little bit of time. Oh. Is it really? Uh-oh. Alright. So the natural language toolkit is not a thing that I have. Oops. Great. Well, anyway. I guess we'll have to move on then. Anyway, yeah. Anyway, that's a big thing. So let's move on to sentiment analysis. So sentiment analysis is a particular type of classification problem that it focuses on trying to determine what the sentiment is in a particular piece of text. There are a great number of applications of sentiment analysis opening up throughout the internet, given the prevalence of social media at the moment. If, for example, you wanted to ban all tweets in which things were spoken negatively, you could, in theory, use sentiment analysis to remove to identify tweets that contain negative sentiments, and then filter based on that or something like that. So I have a question. Are all the updated slides on Avenue for the exam? Pretty sure everything is updated on Avenue, yes. at this point. I think maybe like the first one isn't, but you know, the first one is the first one. So, the basic approach for sentiment analysis is to label individual words as being associated with a sentiment, and then compute a sentiment score for a particular piece of text. The machine learning approach then labels pieces of text as having a particular sentiment, and then uses classifiers to predict a sentiment. So, our approach, once again, is to 1. Obtain labeled data, 2. Construct feature vectors for labeled data using the natural language processing toolkit. Next, divide the data into 2 sets, a training set and a testing set. We train the classifier on the training data, use the classifier to predict the labels for the testing data, and then measure the accuracy of our predicted labels. The goal is to transform natural text into a form that is more effectively processed. This can be this is also known as tokenizing, splitting a passage of text into a list of words or tokens. A token is not necessarily a word; it could also be a phrase. But tokenizing it can be as easy as splitting on space and punctuation, or you can take a more complicated approach. Once you have tokenized, you can then tag the tokens in the passage of text with tags that represent their grammatical role, because that can be determined from the grammatical structure of human language. We can be reasonably sure where the nouns and the verbs and the adjectives are, and of course, this is how things such as Microsoft Word is able to correct your grammar as effectively as it can, because it knows how to recognize a verb and to know when one is not conjugated correctly. We also have stemming, which is reducing words to their root word so that we can identify reoccurrences of the same notion. So, for example, the words happy, happier, happiest, happiness, and happy with an I. Happy with an I would be the root or the stem of that family of words. So it's like taking related words and grouping them together. The other thing that you can do is remove stop words, or commonly used words which don't necessarily contain a lot of semantic content with respect to a sentiment. These are words like prepositions and conjunctions and articles and things like that. The, and, but, was, if, or, was, I, is, me, you, etc., etc., etc. They don't really mean anything in the context of sentiment. They don't convey any sentiment. Within a, human beings understanding human language kind of sense, if you were to remove those words, you would end up with gobbledygook. But, you could still probably get an impression of the sentiment being expressed from the said gobbledygook. Sentiment analysis uses feature vectors and classification. So we construct feature vectors for labeling data by using the natural language processing, using tokenization, stemming the tokens, removing common stop words. We then construct a list of all processed tokens present in all samples, and for each sample we construct a feature vector indicating the number of times each word in the sample is present. We can then run a classification algorithm on each of these feature vectors. So when you do this, you'll end up with, this sentence has a happiness score of 7, a sadness score of 3, and an anger score of -2, or something like that. And once you have performed that type of analysis over a large number, you end up with a large number of vectors, which you can then run your clustering analysis or whatever type of analysis you want to run. Vader is a sentiment analysis tool built into the Natural Language Toolkit. It is already trained to classify passages of English text on positive or negative sentiment. So if you're happy and you know it, clap your hands, comes in at a negative, in terms of polarity scores, negative is 0.0, neutral is 0.7, positive is 0.29, compound is 0.57. So, okay, yes, never mind that. That's all stuff that's not, doesn't matter. So, anyway, and it lets you know who your daddy is. Yes, because it is called Vader. That is a Star Wars joke. We have had a few. But we've had good times. So anyway, congratulations to all of you, all 41 of you who are currently logged in and listening to this. You have successfully made it through Computer Science 1MD3. At least the lecture material, you've got it all now. That's it. So, are there any questions? You can't import NLTK because you probably don't have it installed. If you go over to this guy, this installing NLTK, this slide here, if you're going at it through JHub 2, it'll be on there, hopefully. Otherwise, you will need to use one of these things in order to do that. I don't know. Maybe I can get it to work. I'm actually not feeling great at the moment. PowerShell. Yes. By the powers vested in me, as a person who teaches computer science, I now declare all of the people in this course to be officially designated Chads in the area of computer programming, at least with respect to Python. We have a practical question too. Is there a previous year's exam in order to prepare for the test? What should we do to prepare for the test? Yes, I will dig around and see if I can find something, but please also send me an email to remind me about that. Yes. So anyway, let's see. pip3 install numpy scipy scikit learn. Is that what? No, that's not recognized. Get out of here, you. So Python, it's not Python 3. Pip install numpy scipy scikit learn. Oh. Okay. Maybe that did something. So let's see if this works now. probably have to reload. Stop you. Save. Load her up. Wait, no, I probably have to shut it down completely. Shut it down! Yes. Oh, for pity's sake. Anyway, I would need more time to figure it out. Yeah, so, laptop under pillow learning through osmosis. That's the method I used. So, I've got a serious question. What does the map function do? I'm so glad you asked. So, what map does, it takes a function as an argument and a data structure as an argument, and it applies that function to every element of the data structure. I will define one for you right now. Function, and let's just say we're doing this with lists. For element in list, you know what, might be better with indexes, so I can use assignment. For I in range length of list, L at I is equal to F at L at I, or F of L at I. There you go. So if you have, for example, map lambda x at x plus 3 over 1, 2, 3, and print it. None. That doesn't make any sense. Oh. Yes, it does. There. To your question, machine learning is not going to be on the exam. This was mainly for the sake of interest and coolness and all that kind of good stuff. Yeah, yeah. That was a good show. I was really super into that show when I was a kid. Yeah. Yeah. Anyway, so that's what map does. Hopefully that answers your question. Are there any other questions from the audience this evening? Wake you up. Wake up! There, are you awake? Maybe I can devise other ways of waking you up. The exam's gonna take you 10 hours! Over 4 days! 10 hours each day! I'm just kidding. Or am I? Will the exam be distributed the same way? Yes. Oh, sorry, was that a bit loud? Oh my goodness. sorry. I'm sorry I damaged everybody's eardrums. I'm gonna whisper from now on. So yeah, the exam will be distributed in the same way as the tests and the assignments. You can get it through Jupyter Hub 2, or you can get it through Avenue. Come on, Nick. Everybody knows that this is a text message. This is a text thing. Jeez. Well, maybe you're awake then. Question: will the exam have bonus questions? It will have a bonus question. It will have some number of bonus marks on it, whether that's one question or a couple of questions. That's just gonna have to be, you know, you'll just have to find out. Yes. If if you can explain that, and that is impressive, then you'll know you will have met the one. Just so you know. So, for your question about test 2, please send me an email about it, and we'll take care of it. Oh, I seem I may have lost the picture. There. Looks like we're back. Okay. So, with respect to the Shopee question, if you feel you've been treated unjustly with respect to any question, please shoot me an email and we will get it sorted out. And yes, the Shopee question did expect floating point numbers in the answer. A viable strategy for dealing with that question was to multiply everything by 100, round everything to the nearest whole integer, compute everything in integer arithmetic, and then get back to floating point representation by dividing by 100 and to re-extract the float back out. But yes. So, if there are any more questions, please enter them now. And don't forget to like and subscribe. Like and subscribe. Okay. Normally when people are saying, "Why did I get this test case wrong?" what they really mean is, "Why did I lose the marks for this?" Which usually really means, "Give me the marks for this." But you know, perhaps I'm too quick to judge. Okay. Well, if that's all the questions that we have for today, let me tell you what's going to be going on Wednesday. So Wednesday is our normally scheduled lecture time. Technically speaking, our last lecture, although we have no more material to cover, as we have covered all of it. It will be a review session. So bring your questions. Bring your questions to the review session. I will answer them live on stream. And for all of you who want to see that, there you go. Yes, Wednesday is for exam review. So please bring your questions, otherwise it'll be a very boring session. Although if nobody has anything, I'm sure I can think of something to talk about for at least a little bit. Yes, and I suppose, I guess I should also make a statement with respect to the status of the channel, ? After the review session on Wednesday, I expect the next video series that will be done for this YouTube channel will be the fall offering of this very course, which I am currently not contracted exactly. That's true. I didn't specify COMPSCI questions. I'm not quite to the point of being contracted for it, but I do have. I have been in talks, and I'm going to be the person who is teaching this in the fall. That unless the school is hit by a meteor or something. What is a relatively good continuation for this course? Any suggestions? Yes, we can look at that. So registrar.mcmaster.ca. The kitten is playing. I hope I don't see any of you again. It's my actual goal that all of you manage to pass this course. So let's take a look at the why don't they just make the undergraduate calendar? Undergraduate calendar, McMaster University. COMPSCI, there we go. So, with respect to second-year courses, generally speaking, 2SO3 is kind of considered to be the most direct lead-on from this course. Yeah, maybe I'll put in a bonus question like that. Fundamental concepts of programming: expression, statements, procedures, control structures, iterations, recursion, exceptions, precise memory modeling of traditional imperative language programming languages, basics, data structures, records, arrays, dynamic structures, use of libraries. So that's kind of like, the next level up. I'm not sure what they're using for the programming language in this one. When I took this course, it was C, but I'm not sure. It might be Java or something like that. If anybody in the chat knows what 2SO3, what they teach in there, please shout out. So, for my money, the course that I think everybody should try to shoot for, because it's like, this is the course that will turn you into a computer wizard right here. Data structures and algorithms. It's not an easy one, but if you take it, you will know everything. Basic data structures: stacks, queues, hash tables, and binary trees. Searching and sorting, graph representations and algorithms, including minimum spanning trees, traversals, shortest paths, introduction to algorithmic design strategies, correctness, and performance analysis. A lot of you in the chat have been asking me all... Oh, good Lord. You've been asking me all semester about optimization and how you optimize stuff and stuff like that. This is the course you want to take. However, in order to take it, you have to take COMPSCI 2MD3 first, which is discrete math with applications. So I don't know how many electives you guys have, but, Oh, and this has 1ZC3 or 1BO3 as a prerequisite. Functions, relations, sets, the language of predicate logic, the beautiful music of the universe itself, predicate logic. Propositional logic, proof techniques, counting principles, induction, recursion, discrete probabilities, graphs, and their application to computing. That's the math that I do for my thesis, just in case you were wondering, that kind of stuff. Yes. Going on from there, functional programming, sure. Although I think there's a first-year version of that. Yes, I think Introduction to Computational Thinking is essentially, they run that as a Haskell programming course. So you know how I've been singing the praises of my favorite programming language all semester. I believe 1JC3 is the course in which they teach it. Inquiry into ideas and methods of computer science, the science underlying our computational universe. Topics include what computers can and cannot do, the internet and search engines, artificial intelligence, computer-controlled devices, and sustainability in computing. There you go. 1XA3 is, I believe, well, maybe I'm mucking this up. I'm not sure, but yeah. So for this one, you have to be registered in computer science anyway. So, yep. Anyway, so there are some courses you can take from here. Information security would be interesting. It's a course on cryptography. Cryptography is really cool. It's like so nerdy and so cool. I love it. If you want to take a really interesting and cool course, there's an optimization course right there. Fourth-year optimization course, though, that would be super hard. I'm just saying. There's a reason it's a fourth-year course. Fundamentals of image processing is a nice, cool course as well. Yeah, unfortunately, you have to be, registered in the program, so that's probably not going to work for you. But notice the prerequisite for linear optimization is the algorithms course that I was talking about. Introduction to Machine Learning. If this last lecture interested you, then perhaps that would be interesting to you too. There you go. You can see that a lot of the topics we talked about are just straight up a course in 4th year. But like databases and advanced databases. But yeah, anyway, maybe that answers your question. Are there any other questions for me this evening? Cool. Yeah, so in summary, if you're serious about studying the coolest stuff in the world with respect to computing, see if you can make it to this one, because man, that is just the coolest stuff ever. If you liked the bits where we were talking about changing algorithms into logarithmic algorithms and stuff. Ooh, question. Can we see Martin? He doesn't get the same recognition as Marimba. Very true. I'll go grab him. All right. Hello, all. Martin has arrived. Say hello to the nice people on the internet. I know you want to get... Oh, the little one has come as well. You have to look at the camera, though. I know you guys. Kissing kisses. Yeah, I know. But can I get you to look at the camera, even just for a second? Can I get you to look at the camera? Looking at the camera? Well, anyway. Yeah. I mean, actually, we had him to the vet a week or two ago, and he's actually a little bit on the chubby side because he's been eating kitten food, and if you know anything about kitten food, it's slightly denser in terms of calories. Oh my gosh, the little one's running around too. So, you know, he just needs to get back on his regular food. There we go. Anyway, yeah, he's cool. Martin's a cool cat. Anyway, that's it. I guess see you guys on Wednesday. Take her easy, folks. Don't do anything I wouldn't do. Oh, and tonight's the last tutorial. So, have fun with it. Ask plenty of hard questions. I love to see the TAs exercised. See you, folks.